Good morning. Today we'll discuss about the differential equation method for determining the impedance which is required for distance protection of transmission line. In the last lecture, we have started with the distance protection. The principle of operation, we have seen that if the measured impedance is less than your preset value, then a relay will initiate a trip signal. And we have seen that distance relays offer many advantages when compared to overcurrent relay. The important one is the impedance relay is fast and most of the times it is instantaneous. And distance relays are widely used for protection of transmission lines. So based upon the length of the transmission lines, we do call them as impedance relays, reactance relays, Moore relays for small, medium and long transmission lines. And in all of these methods, we are supposed to determine the impedance. And this is obtained from V and also I. So V and I are continuously obtained from the transmission system. They will be sampled and the digital signals are processed to the computer. And this computer, it extracts the V and I, the fundamental components, RMS values of V and I, and based upon that, the ratio of V and I will be your measured value of impedance, and it will be compared with your preset value of impedance, and if it is less than the preset value, then your relay will initiate a trigger signal, trip signal. This is how your distance relay, numerical distance relay operates. And we have seen a particular method called as a Mann and Morrison method for extracting the impedance from the available samples of voltage and current. In today's class, we will discuss about the differential equation method. This differential equation method is also used for extracting impedance from available V and I samples, voltage and current samples. So today we will learn about how to determine the impedance from available voltage and current samples. So I'll start with the introduction to distance protection. A quick review. You know that distance protection is widely employed for transmission lines. It depends upon the distance of the feeding point to the fault. And it is a function of, the impedance is a function of ratio of voltage and current, and based upon the impedance value, the time of operation will be varied. And the different types of distance relays are impedance relay, reactance relay and the Moore relay. So these are the widely employed relays for protection of transmission lines. And coming to the differential equation method, it is a method which is used for implementing numerical distance protection. It basically involves solving numerical equations. We will be having few assumptions before we start the differential equation method. So based upon that assumptions, we will develop a model of the transmission line, and based upon that, we will determine the impedance. And in particular, the differential equation method, it's involves solving differential equations that model the behavior, and in particular it involves using phasor measurements of line current and line voltage. In fact, it employs sample values of V and I, and based upon that the impedance is calculated, and in turn the impedance is compared with the preset value. Coming to the operating principle, you know that under normal operation the impedance of the transmission line is relatively constant, isn't it? However, when a fault occurs, automatically the impedance changes due to the fault resistance, fault location and the inception angle also. So these changes, particularly the change in the impedance, it will be recorded, and the differential equations which are used here, they will be typically solved in the phasor domain. And based upon that, impedance is determined and then it is compared with the preset value. And then very similar to that of the Mann and Morrison method. method. Here also, once the impedance is determined and compared, we will be using 3 zones of protection. Now, we will move on directly to the mathematical modeling of the differential equation method. But before that, the biggest advantage of differential equation method when compared to the previous Mann-Morrison method is that we will be able to accurately model the behavior of the transmission line during fault conditions. We will be considering the resistance and also the angle of the impedance also. So it helps us to determine the accurate location of the fault. But there is a problem. It requires a little bit, it is a complex method because it requires solving complex differential equations when compared to the earliest method. But after solving this particular thing, I think you will be able to say that differential equation method is good when compared to the other methods. It all depends upon what type of assumptions you will be taking. In this particular lecture, I will be considering the transmission line as a lumped series RL circuit. So whatever the transmission line which you do have, let us suppose I'll take this is the transmission line. I'll take that normally your transmission line will be extended over lengths, kilometers of lengths. So it will be having R, it will be having L, it will be having C, it will be having G, all the 4 parameters it will be having. And normally all these elements are basically distributed. This is what happens in practice. But since because of my limitations, computational limitations, I am considering only R and L, that my transmission can be represented with R and L, and that too I'll assume that these are lumped elements. Okay, so I am going to eliminate the distribution, the distributed phenomena. I'll assume that everywhere R and L are concentrated only in one place, and I'll also neglect this shunt components, conductance and also capacitance. Okay, so based upon this particular assumption that a lumped value of R and L is available, so I can model my transmission line like this: R and L. This is your sending end current with the sending end voltage, and this is the receiving end current with receiving end current. So this is the simplest assumption which I will be taking. So see here, this is the transmission line. Now this is my generator. Here I will be measuring my current CT, and this is my PT. Both will be fed to my relay, and relay in turn gives a signal which will be given to your circuit breaker, which will be tripping the circuit. Okay, so this is my mechanism, operating mechanism, and see this is the transmission line which is represented by a simple R and L in series, and I'll assume that at this particular point there has been a fault. Okay, now let's try to write down the differential equations for this one. So now considering a single phase transmission line, one more assumption, I'm going to consider only single phase transmission line for your class. Okay, so I'll assume that there is a ground fault at a certain distance x from the sending ends. This is what I have shown. This is the distance from the sending ends. Okay, and let the current and voltage be V and I. Okay, let the current and voltage be V and I respectively at the location where this is the location of my relay, and this is my fault location. At the relay location, my currents are V and I. Okay, so if my you know that this is V, since it is a fault, the current will be directly, that line will be directly grounded. So you know about KCL and KVL, right? I'll apply the KVL. See, V is equal to, this is the voltage drop here is IR plus JIXL, in plus there is a direct short circuit, so I'll take it as 0. If in case if there is any impedance, then I'll take it as IZ. This is the fault impedance. But in this case, I am directly considering. So if you want to write it in the form of differential equation, I'll directly take it as LdI by dt. This is a time domain type of equation. Right. So this is the equation. the governing equation. V is equal to R and L are the resistance and inductance of the transmission line, lumped parameters. V and I are the voltage and currents at the relay location. Now, see. Now, these are the sampling instance of my voltage and current. Now, let us suppose this is the V and this is I. So, I am sampling them. These are my sampling instance. Okay. Now, I do have this particular equation, right? I'll write it here. V is equal to R I plus L di by dt. Now, if I take two different samples, this equation must hold good for any number of samples. So, I'll take nth sample. If I take n plus 1th sample also, the relation must hold good. Right. So, this is what I have written here. Nth sample and also for n plus 1th sample. In this equation, if you carefully see, this is din, right? What is din? You know, it is d by dt of in, or I will call it as in dash. We have seen yesterday how to compute this. This I can write it as, if I take two samples, not adjacent samples, separated by at least two time intervals. Right, this is in dash, or what I call it as din by dt. If I take in plus 1 sample, so what it will be, this is n plus 2 minus in by dn. This is this particular equation. So if I replace, see, these are the, right, if I do have samples like this, this is n minus 1, this is n plus 1, this is n plus 2, this is n plus 3. So if I want differential here, what I am doing is I am considering these two samples, in plus 1 minus in minus 1, by the between two samples, the distance is delta t. Here delta t, here is delta t. So totally it is 2 delta t. This is what I have considered here. Okay, if I want to take differential at this particular point, so I am going to take the adjacent samples, n plus 2 minus n by 2 delta t. So now I am replacing them in the original equations. Vn is equal to Rin plus, here it must be actually din by dt, that I am replacing it here. Here it must be din plus 1 by dt. Now if you carefully see, if I write them in matrix format, see here, this is V, this is V. Now see,